to the 0.01t. Then what? Natural log of both sides. So I've got the natural log of 1.7 equals 0.01t times the natural log of e. What can I go ahead and do at that point? Okay, and before that even, the natural log of e cancels out. And then so to find our answer, we're going to take the natural log of 1.7 and divide it by 0.01. And that'll give us the time at which it's going to take for that population to reach the 17. So the nearest hour, what are you getting? 53. We're going to say approximately 53 hours. So for there to be an extra 700 bacteria, it's going to take 53 hours. Which really, considering that it's almost doubling, that's not really that long, is it? Pretty quick. Things like bacteria do grow pretty quickly. Last question is one I want you to try on your own. Give this a raise. So this is yours. What is this part? F or E? Okay. For F, your question. When will the population double? When will the population double? So I want you to try to figure that out for me, okay? Keep in mind, this works a lot like the ones that we did with interest. In fact, exactly like the ones we did with interest. So think about how we set those up. Do the same thing. Any volunteers come up here and write out what you set up to solve? We still need some more time. Volunteer. Justin? You want to tell me? What did you plug in for NFT? Okay, because we knew the initial amount was 1,000, so when I asked for it to double, it'd be 2,000. We got an actual number. So we're just going to plug in and out exactly like what we did before. 2,000 is going to equal 1,000 times e to the 0.01t divide, and we're going to get what we think we should get. We're going to get a 2 over here. So 2 equals e to the 0.01t. Natural log of both sides, so the natural log of 2 equals 0.01t times the natural log of e. Like we've already looked at, the natural log of e, since the base is the same thing as what we're taking the log of, it does cancel out. So then take natural log of 2 and divide it by 0.01. And we're going to get our time. What? 69. Okay. It's about 69 hours. So does that answer make sense based on the last one we did? Yeah, so just a little bit longer than what we already had for 1,700 hours, which makes sense. So you'll have a couple in your homework that are just like that, same kind of questions, same kind of stuff. Okay? So this was a case where we actually had the equation to begin. The next one we're going to look at can be a little bit different. This is a kind of more realistic problem. And we're going to pretend like we're scientists. We've got some data, and we're going to use that data to come up with the function on our own. We're not given it yet. And then we'll use that function to answer the question. Just in case you're curious, the picture up there is of the cholera bacteria. You know what that is? Not so good. You can probably imagine why, in case of bacteria that are harmful to people, why it would be important to know how fast they grow. Based on that, antibiotic treatments, figure out how much antibiotics you need to counteract the growth of bacteria. All kinds of good stuff like that. We've got a culture of bacteria that obeys the law of uninhibited growth. Yet 500 bacteria are present initially, and there are 800 after 1 hour. First question, how many will be present in the culture after 5 hours? And the second question, how long until there is 20,000 bacteria? What we have to get first is that function, since we don't have one. So we're going to go back to the uninhibited growth law, plug in what we know, and then figure out what we don't know. So in this case, I know the initial amount, and I know the amount after 1 hour. So I'm going to say that 800 equals the initial amount, 500, times e to the, I don't know k, I don't know the rate, but I do know time is what? How long? 1 hour. Which is 1, makes the work a little bit easier. Or we can do it with any amount of time. So now we're just going to solve this for k, and we're going to do that just like we did when we were solving for t last time. That's an exponent with a variable. So divide by 500. So I'm just going to leave that as a fraction for right now. So 8/5 equals e to the k. Take our natural log, and this one's going to work out very nicely. The natural log of 8/5 equals k times the natural log of e. So the natural log of e goes away. So k equals the natural log of 8/5. 0.47. Yeah. What is k? What's that been on all these? The growth rate. So this has a 47% growth rate, which is a lot faster than our other one. Does that look like it's a valid answer? Yeah, if you look at this, okay, we had 500 to begin with. After 1 hour, it's already up to 800. It's a pretty big jump. So that seems like a valid answer for us. Now that we've got that, we've got the function. So I'm going to go ahead and write that out. In general, n of t is going to equal our initial amount, which was the 500, to the e, now I know that amount, 4.7 t. But we figured out the constant, we figured out the growth rate, plug that in with the initial value, and now we've got our function just like what I gave you on the last loop. So now we can answer our questions. First one, to figure out how many are there after 5 hours, we're plug in 5 for t. So we're going to find out that n of 5 is equal to 500 times e to the 0.47 times 5. So just plug that right in your calculator. Let me know what you get. Let's see it. So let's go nearest bacteria. So about 5,000, say it again. 5,000. And you can see why this is good stuff to know. That is a huge increase. It started out with 500. 5 hours later, it's already up to 5,000. So it's growing very, very rapidly. Since it's a bad bacteria, cholera is definitely not something going around. It's spreading pretty quickly. So it's good to know that kind of stuff. The next question, solve that on your own. Find out how long it's going to take to get up to 20,000. You already done one like that. Why don't you try it on your own? My work's up there now. That matched up. Go ahead. What did you come up with? Say again. 7.8. And our unit would just be in hours again.